Hello everyone, I'm Ettore Lamacchia and I work with Eric Exton, Alberto Pereira and Paul Weaver. The title of my presentation is Morphing Structures, Nonlinear Composite Shells with Irregular Planforms. And the aim of this project is to develop an accurate and computationally efficient model to describe the multistable behavior of thin composite shells with irregular planforms for morphing applications. And to do that, I developed a semi-analytical model and writing the total strain energy as we see in this equation using the classical laminar analysis and linking in a linear fashion the in-plane strains and the curvatures. And here we can see the contributions also of any inelastic field. It can be temperature, it can be moisture, it can be piezoelectric. And as we see, we use von Karman nonlinear in-plane strains, but the key point of this model is the coupling of the total strain energy in its bending and membrane contributions by using the pseudo-inverse semi-inverse formulation of the constitutive equations, which links in-plane strains and to the in-plane stresses, resultants, and curvatures. In this way, we can decouple the total strain energy. As we can see here, the stiffness matrix is now a diagonal matrix. And we got the a linear combination of the membrane energies plus the bending energy and the inelastic contributions. And we do that because we can solve separately the two problems. And in particular, we solve the membrane problem combining the compatibility conditions, which links in-plane strains and curvatures according to the Gauss theorem egregium, and the in-plane equilibrium equations plus boundary conditions. Again, by using the semi-inverse formulation of the constitutive equations, we can substitute in the membrane problem the in-plane strains function of the in-plane stress resultants and curvatures, obtaining in-plane stress resultants which is now a function of just the curvatures. And by substituting back in the total strain energy the in-plane stress resultants, we got a total strain energy which is now a function of the curvatures, and the Hessian of the energy with respect to the curvatures gives the stability positions. We solved the membrane problem by using the differential quadrature method, which is a pseudo-spectral method which consists of expressing the derivative of a function in each point of the domain as a linear combination of all the functional values of the domain that multiplies weighting coefficients, which are defined by using shape function defined in the overall domain. This allows the membrane problem to be solved accurately and using fewer degrees of freedom compared to most more common numerical methods as finite element or finite difference methods. In particular, we use the matrix formulation of the differential quadrature method because if we recall the membrane problem, we introduced three differential operators L1 and L2 and L3, which we recast in a global differential operator that we call L. That's what we discretize using the differential quadrature method, so that the in-plane stress resultants can be found by simply inverting a matrix of weighting coefficients. And in particular, we use the Moore-Penrose pseudo-inverse operation because the differential operator L is a rectangular matrix since it takes into account also the boundary conditions. It's interesting to observe that the differential operator L is in particular L1 is a second order differential operator in X and Y, which means that when it's applied to the external inelastic field, the Gaussian curvature does not change if the external field is constant or linear in X and Y. And we can visualize this by considering an isotropic cylindrical shell and tracking the displacement of the two cross-sections, the blue and the red one, under the action of a constant or quadratically varying thermal field. And we see that the initially curved cross-section deforms both in plane and out of plane, regardless the distribution of the thermal field, whereas the initially flat cross-section, the red one, that forms just in plane after under the action of a constant field, whereas it deforms also out of plane when an external quadratic field is applied. This means that the initial cylindrical shell deforms by changing its Gaussian curvature to accommodate the inelastic stress if the external field is at least of the second order in x and y. So we got our model, we validated with benchmark results available in literature, and now we apply it to model a morphing passive chevron for noise reduction. This is a concept proposed by Eric Exton recently, and it consists of a hybrid aluminum carbon fiber chevron, which morphs between two configurations, the low noise configuration and the low drag configuration, by exploiting the mismatch in thermal expansion coefficients of the two materials and the thermal field of the jet exhaust node flux. And this allows us to create a passive thermal actuating morphic structures without any need for actuation. In order to model that, we have to generalize the proposed model in order to deal with non-regular planforms. And to do that, we introduce what is called the blending function, which is a linear function which essentially maps each point of the physical irregular domain to the corresponding point in the regular computational domain by essentially expressing the four edges and the four corners of the physical domain in terms of the coordinates of the regular computational domain. And we end up by finding a mapping law which is this one, that we applied to all our governing equations, strains, curvatures, compatibility condition, equilibrium equations, by bearing in mind that the boundary conditions always have to be applied to the physical domain. The advantage of using this technique is that we can deal with irregular planforms without increasing the degrees of freedom of our model. So, some results: we got our jet engines with the chevron in its position, and we start from the low drag configuration, which is a cylindrical shell. By increasing the temperature, slowly the chevron morphs towards the low noise configuration through a series of intermediate states, and until the low noise configuration appears, which is a cylindrical shell orthogonal to the initial one, and the chevron keeps this configuration until we decrease the temperatures, so that it morphs again through the series of intermediate states towards the low drag configuration. And this is a process completely passive and reversible, because we can increase and decrease the temperature, and we morph in between the two orthogonal cylindrical shells. So to conclude, we propose an accurate and efficient computational model in order to describe the multistability of thin composite shells with irregular planforms. We apply our model generalizing the governing equation to deal with non-regular planforms. And further investigation will look at generalizing our model to deal with general doubly curved shell with any initial curvatures. And also it's interesting to investigate the nature of the inverse of the differential operator, which is essentially an integral operator. And the kernel of the integral operator is the green function associated with the membrane problem, and this allows the designer to find quick and accurate solution for the membrane problem. Thanks for your attention. If you'd like to contact me, this is my mail. I would like to thank my sponsor for the support in this research. Thank you.